Welcome. I would like to explain the problem of geodesic on a sphere. This is an important application to the calculus of variations. This presentation is based on the textbook below. It's a very nice textbook, and it would be nice if you could review more in the textbook itself. Before starting, the first thing to do is to explain what's a geodesic. You can refer to this link from Wikipedia. The geodesic is referred to, or it represents the locally or the shortest path between 2 points on a surface. Okay, this is a generalization of what's so-called a straight line. To be more explicit, consider this flat plane surface. For any two points on this surface, the shortest path between these 2 points is a straight line, as we know. Okay, so the geodesic is a generalization for this concept. Our aim here, or the aim here, is to clarify the geodesic on a sphere. It is clear, as you could see, is that for a sphere, the situation is different because for a sphere, you have a curved surface, you do not have a flat surface. So suppose you are having 2 points on a sphere, what is the shortest path? I'm trying to clarify further by using this globe, which is for the Earth. Of course, the Earth has a spherical shape. And this spherical shape is usually described in terms of what's so-called the latitude circles and the longitude lines. Okay, these are the latitude circles and the longitude lines. Please observe that the longitude lines are also circles whose center is the center of the sphere, which is not the case for the latitude circles. Let us examine this situation right now. Suppose you are planning to have a direct flight between these two cities from Turkey to Spain. Both cities almost lie on the same latitude circle. Okay, what is the shortest path to be selected by the pilot? For instance, shall the pilot just follow the latitude because they are on the same latitude? Is this the shortest path, or there is another shortest path? Okay, this is the problem that we are trying to solve right now. I'm sorry, I will spoil the problem, or I'll spoil the solution. The shortest path between the 2 points will be what's so-called the great circle, an arc of what's so-called the great circle. Fine? So what's the great circle? The great circle is the circle on the surface of the sphere whose center is centered at the same center of the sphere. Okay? Again, we have mentioned in the last slide that for the longitude lines, these are arcs of a circle whose center is the center of a sphere itself, as depicted here. However, this is not the case for the latitude circles. For the latitude circles, as you could see, the center may be above or below the center of the sphere itself. Okay, so the latitude circles are examples for what's so-called the small circle, and the longitude circles are examples of the what's so-called the great circle, whose center is the center of the sphere. So the solution, or the geodesic, will be a great circle. How could we derive that? To derive that, we will use our team. Our team here will be the set of coordinates for the spherical coordinates, which are r and theta and phi. By the way, phi, as you may observe, is the longitude that is used by Google Maps, and the theta, it's like the complementary of the latitude that's used by Google Map. Okay, by the way, Google Map also does not display r because Google Map is assuming that you are traveling on the surface of the Earth, hence your r is constant, which is equal to the radius of the Earth. It is important to draw your attention to the transformation between r, theta, phi, and x and y and z. Let us focus on this second transformation. Given r and theta, phi, you can get x, y, and z. For instance, this is r and this is theta between the vertical axis and r. If you draw this perpendicular line, you will have a right angle triangle, and the hypotenuse is r, and the adjacent here is z, which is equal to r cosine theta. For the other end, which is the opposite, it is this side, which is equal to r sine theta, which corresponds to this line here in the xy plane. And this line, which is r sine theta, can be further projected by cosine phi to get you the x and by sine phi to get you the y. Again, now we are ready to refer back to our problem, given 2 points P1 and P2 that lie on the surface of a sphere. Okay, P1 and P2 that lie on the surface of a sphere, we need to find the shortest path. This shortest path minimizes S, where S is equal to the contour integral from P1 to P2 of ds. ds is called an infinitesimal line element length. This infinitesimal line element length is somehow straightforward to deal with in the flat plane. Okay, in a flat plane in Cartesian coordinates, suppose you are having 2 points that are infinitesimally close to each other with horizontal separation dx and dy. Since dx and dy is perpendicular, then ds is equal to the hypotenuse, which is the square root of dx squared by dy squared by Pythagoras theorem. It's somehow complicated to derive something similar using d phi and d theta. Okay, for d phi and d theta, assume that you are having an infinitesimal displacement in the direction of phi and an infinitesimal displacement in the direction of theta. Okay, we will derive each one of these separately. Focus on the displacement in the direction of theta. When we are making a displacement in the direction of theta, we are moving on a longitude line or a longitude arc or a longitude circle. This circle is a great circle, hence the radius is equal to the center is the center of the sphere, hence the radius is equal to the radius of the sphere. And since we have made a small displacement d theta, the arc length, this one here, will be equal to r d theta from the ordinary or from the school geometry. So this is r d theta. What about the second one? The second one, which is described by having a small displacement in phi, we are moving on a small circle, okay? For what is the radius of the small circle? The radius of the small circle, as you may recall from the last slide, is equal to r sine theta. It is not r cosine theta, it is this line which is r sine theta. So the radius of the small circle is r sine theta. Hence, if we are going to make a small displacement by d phi, the arc length will be r sine theta multiplied d phi. So we identify the lengths of the two infinitesimal lines, r sine theta d phi and r d theta. Hence, ds, using again Pythagorean theorem, is equal to the square root of the squares of both of them. Now we are ready to calculate s as equal to this square root, and we need to choose either phi as a function in theta or theta as a function in phi if you have any experience with the calculus of variation. Due to experience only, we will choose phi to be a function in theta. Hence, we will get d theta outside of the bracket, d theta squared. D theta squared outside is a d theta. You are left here with r squared alone, sine squared d theta, and d phi by d theta the whole squared, which is equal to phi prime squared. And again, I have taken r outside. Now we have this form. The integral is equal to some function f capital, that's function in phi, phi prime and theta. Phi prime and theta, and we will discuss why phi is missing. The calculus of variation tells us that to get the shortest path or the shortest value for this integral, we need to solve the Euler-Lagrange equation written in terms of partial f by partial phi minus d by d theta partial f partial phi prime. Hence, our focus is the integral itself, the integrand itself. This is the integrand written again. As we have already mentioned, phi is not appearing explicitly, hence partial f partial phi is equal to 0, and this is partial f partial phi prime. You can verify this manually. Euler-Lagrange equation, I am just rewriting it again here. Again, partial f partial phi is equal to 0, hence the time derivative of, the full derivative with respect to theta of partial f partial phi prime is equal to 0, hence this partial f partial phi prime itself is equal to a constant. We need to isolate df by d theta. To do this isolation, then due to technical reasons related to maxima, the I will share the file in the comments. Due to technical issues, I had to square both sides and get, by the way, this is the quadratic equation, that's why we are having two solutions. I will use the first solution. I will use the trigonometric identity cosec squared theta is equal to 1 plus cotan squared theta, and then I will apply the integral. Remember that this is d phi by d theta, hence when we integrate this one we will get phi as a function in theta. And I will use the substitution q is equal to phi cotan theta, we will get this kind of expression, and I will substitute by phi is equal to k over square root 1 over k squared, and k will cancel from the numerator and the denominator, and we will get this form. And if you remember from the elementary calculus that this is the square root of 1 minus q squared, which is integrated to be sine inverse q. Hence phi is equal to sine inverse q plus the integration constant. Or if we take the sine for both sides and get beta in the left hand side, we'll get phi sine phi minus beta is equal to q. Remember that we have used the substitution q is equal to alpha cotan theta, hence alpha cotan theta is equal to sine phi minus beta, and I will multiply both sides by sine theta to get rid of sine theta in the denominator of cotan theta, and we get here a cosine theta, and then I will expand the right hand side to get sine phi minus beta is equal to sine phi cosine beta, and so on. This is trigonometry from the elementary mathematics, and then I will expand the right hand side. And now it's time to refer back to the transformation. R cosine theta, if you remember here, it was equal to z. R cosine theta is equal to z. Okay? R cosine theta is equal to z. And by the way, please revise the transformation. You will realize that R sine theta sine phi is equal to x. And you will realize that R sine theta sine phi is equal to x. So this is the equation that we have got for the geodesic in terms of the Cartesian coordinates x and y and z. You may feel amazed why we are referring back in the Cartesian coordinates. I will explain shortly. We need to review quickly the equation of a plane, the Cartesian equation of a plane. The Cartesian equation of a plane is written in this form: ax plus by plus cz equal to x and y and z are the coordinates of any point that lies on the plane. In other words, any point on this plane must satisfy this equation. And just for your information, A, B, and C are the components of a vector that is perpendicular to this plane. A special case of this equation when d is equal to 0. We will find this form, ax plus by plus cz equal to 0. This is an important special case because for this special case, the plane passes by the origin. If you substitute here by the coordinates of the origin, x equal 0, y equal 0, z equal 0, you will find that the equation is satisfied. By the way, this equation is not satisfied by the origin point. If you substitute by x0, y0, z0, you will get d equal 0, then the equation is not satisfied, but it is satisfied here. So briefly, this is the equation of a plane that passes by the origin. It is very similar or identical in form to this kind of equation that we have derived for the geodesic. You can, for example, observe that y, the coefficient of y cosine beta here is b, the coefficient of x here negative sine beta is a, and of course if you get z alpha to the right hand side, it will be minus z alpha, and the coefficient of alpha negative alpha is equal to c. So we have concluded that the geodesic is the intersection of a plane that passes by the origin with the sphere. If you hence the geodesic is a great circle. Okay, why? Because the center of a great circle is the center of a sphere, and we have already mentioned that the geodesic is the intersection of a plane that also passes by the origin. Hence, the geodesic is the great circle that passes by the 2 points. Thank you very much for your listening.